Hi, chemistry. Welcome back to the mole hole. I wanted to talk a little bit today about things we're not going to find on the mole hole, or maybe tricky things we're going to find on the mole hole. First of all, let's talk about why we call this the mole hole. It seems like a strange name. Other people call it other things like the mole train. But if you look at this as if it's ground level, right, we can add like trees in here and maybe a giant flower. Okay, so we're talking about moles. They are spelled conspicuously like the little animals that tunnel in the ground. But don't look anything like that. Okay, maybe something like that. Anyway, you can look at it as a tunnel system, right? And if the moles have a tunnel system, they can get from one room to another room as long as they follow the tunnels, right? However, they cannot get from one spot to another spot if there's no tunnel. So that's the nature of this graphic here, is it shows you the allowable paths, right? If we're in particles, we can convert into moles, but we can't convert straight into grams, right? We'd have to first convert into moles and then convert into grams, much like a tunnel system where you can't just jump or teleport from one room to the next room. You have to follow the hallways that are present. Same thing with this graphic. Okay, so that's why we call it the mole hole, in case you were wondering. Let's talk about what's not on here, or what is kind of on here, but it's a little tricky to see. So first of all, this conversion between compounds and atoms. Let's say we have water, right? H2O is our formula. So water is going to be our A, right? Well, there is a conversion between water and, let's say, hydrogen atoms. So water molecules or hydrogen atoms. Okay, so yes, here, if this is water molecules, and that's our A, right? That's this side. And then oxygen, that's our B. It's feasible that we could go from water molecules to moles of water to moles of hydrogen to hydrogen atoms. That's possible, but there is actually a direct conversion from water molecules into hydrogen atoms, right? Remember, a conversion factor is just a ratio that shows you the relationship that exists. Well, there is a relationship that exists between water molecules and hydrogen atoms. For every one water molecule, how many hydrogen atoms do we have? We have two, right? And we can see that in the subscript that's present. And so that's what this line is all about. This line is a direct path between a compound or a molecule into, I guess I switched on us here. Let me correct this. We're not talking about oxygen, we're talking about hydrogen. Okay, so this is the direct link between molecules of water and then atoms of hydrogen, right? This conversion factor is going to be the formula, the chemical formula will tell you what this ratio is. So for every one water molecule, we have two hydrogen atoms. That is a true conversion factor. The top is equivalent to the bottom. We have two different units, and it can be written as an equivalent statement, or it can be written as a fraction that's equal to 1. So this is a direct link that is on this mole hole graphic, but it's kind of tricky to see, right? It's really easy to miss. Okay, the other thing A couple other things that are on here. I want to talk about where density would go. So we've talked about density as a conversion factor, right? Density tells you how much of something is in a given amount of space, right? It's going to be mass of that something over total volume. So we're going to get units of grams per liter. Well, if you notice on here, grams is on here. Yes, it is. Liters is also on here. So remember, we can have liters of a gas. That would be 22.4 liters per mole as long as you're at STP. We can also have liters of a solution, of an aqueous solution, and that would be molarity, right? Well, we do have grams and liters. So technically, we could connect these two with a line because density is our direct conversion factor between these two. Density is our conversion factor between grams of a substance and liters of that substance. Usually, if we're talking about density, we're talking about a solution. We can be talking about a solid. We can also technically be talking about a gas, probably not a STP. But we do have this direct connection between liters and grams. Now, why don't they put a connection here? Why don't they have that line in there permanently? Why don't they display density here? Well, it's because density is not something that we can easily find. Look at all our other conversion factors. Okay, we just talked about the conversion factor for this line being the formula. That's easy for us to see, right? All we need is the formula, and we would have the formula if we had a reaction or if we had the name. So in order to talk about know what we're talking about, we have to have the formula, right? The conversion factor here is Avogadro's number. Avogadro's number is probably something you have memorized at this point in time. It's a really famous number. It's a number that all chemists are just going to know off the top of their head anyway. And so that's a really accessible piece of information. Same thing with 22.4 liters, right? It's a known value. It's a famous value. It's a value that most chemists are going to know off the top of their head. So it's a really easily accessible value. And then these two numbers also, Avogadro's number and the molar volume, are consistent. They don't change. Avogadro's number is a number of particles to moles for anything, for water, for hydrogen, for golf balls, for donuts, for elephants, right? It's a consistent number. It is the number of that group. It doesn't change depending on what you're talking about. Same thing with 22.4 liters. It's consistent for any gas that you're talking about. It doesn't matter if you're talking about gaseous water or atomic oxygen or molecular oxygen, right? That number is very consistent, so it doesn't change. The only thing that really does change, depending on what you're talking about, is molar mass. The only conversion factor, I should say. Molar mass is going to change. Molar mass for water is 18 grams per milliliters. Molar mass for oxygen, a molecule of oxygen, is 32 grams per mole. So molar mass does change depending on what you're talking about, but it's easily accessible because where is it? It's on the periodic table, right? We're going to have a periodic table with us. It contains so much information that we need anyway, so we can easily access molar mass by looking at a periodic table. Well, none of these things are true for density. Density changes depending on what you're talking about, so it's not consistent. Density also is not on the periodic table anywhere. So in order to know the density of a substance, we either have to measure it or we have to go to a reference book like the Merck Index and look it up. And that is difficult to do. And so that's why they don't put density on this graphic. But if you know the density of a subject, then you can create your own connection between grams and liters of that thing. So there are some other things that are like that as well. If you can measure it, you can use it, right? We talked about conversion factors before and how if we can write it as an equivalent statement, we can use it. Well, the same thing is true. If you can measure the molecules per gram of a certain substance and you know what that relationship is, you are allowed to use that as a conversion factor, even though it's not on this graphic. So remember that this graphic is supposed to be helpful to you. It's supposed to be a really good reference, but it's not the end all be all of conversion factors. There are more conversion factors than exist in this graphic. So just be on the lookout for those. We have a couple of them on our flashcards, like density, this one with the formulas, and also our SI units, right? You are allowed to use those as long as you can write it as an equivalent statement as well. Okay, so just wanted to throw that piece of information out there, give you something to think about today. Let me know if you have any questions. I'll see you in class.